All right, so next up, let's go ahead and do some actual problems with trig. So what we're going to do is solve some triangles. And what I mean by solve is really we're going to be finding all missing sides and angles. So let's go ahead and take a look at some examples. Let's do a problem. Let's have a right triangle. Let's do 32 degrees here. The opposite side is 50. And so we don't know what this angle is. I'll call it angle A. I don't know what this side length is. I'll call it X. And I don't know this side length either. So this will be X and Y. All right. So to begin with, it's actually probably the most straightforward to solve for A, because the angles in a triangle have to add up to 180. And really, we already talked about this. You don't even need that 90. All you really need is that these add up to 90 degrees. And so if we do that and solve for A, we should end up with 58 degrees. So we're already 1/3 of the way there. Now for the side lengths, we might think, well, the Pythagorean theorem could help us. So if I did y squared plus 5 squared, I should get x squared. The problem is there are two unknowns here, so we're not going to use that yet. What we're going to do first is trigonometry. So there's a couple of different options. I could use sine because I have the opposite, and then I would solve for the hypotenuse, which is x, or we could use, tangent, because we have the opposite, and then that would let us solve for the adjacent side, which is y. So it really doesn't matter what you want to do. I'll probably just use sine in this case just to solve for x, but just know that you could do either one. All right, so let's come up here, kind of contain everything in the same spot. So I'll go ahead and put it up here. So I'm going to write down the equation that I know. I know that sine of 32 degrees equals the opposite over the hypotenuse, 5 over x. Now solving for x, I'm going to multiply it to the other side, and then I'll divide both sides by the sine. Let's go ahead and use our calculator here. 5 divided by sine of 32. Now notice I am going to have an issue here because I'm in radians mode and I'm using 32 degrees. So let's go ahead and switch to degrees. Notice how the answer actually does change. Not a lot in this case, but it does change. So we'll do 9.435. Let's just do one decimal place. So we'll say 9.4. And now I need to solve for y, so you could use the Pythagorean theorem at this point. So we could actually say y squared plus 5 squared equals x squared, which means y equals the square root of x squared minus 5 squared. Remember, x is 9.4. So let's go ahead and go to our calculator again. I want to avoid any rounding issues, so I'm just going to click this ans button that's below the 3. And notice it actually gives me the full answer rather than just 9.4. So we'll square that, subtract 5 squared. Now I want the square root, and I'm going to use the answer button again below the 3. And so I get about 8 in this case, 8.0. That's it. So I have my answer. A is 58 degrees, x is about 9.4, and y is 8.0. And that's really how these work. We can do another one really quick. Pardon the interruption. Okay, so we could do another one. Let's go ahead and set up a different one. I'm going to sort of change the orientation of our triangle in this case. That's right triangle, even though it doesn't look like it, it's not drawn to scale. I'm going to say the hypotenuse in this case is 17. And we're going to call this angle here 78 degrees. So notice the opposite is actually over here, so we could call that x if we want this time. The adjacent side is actually this one, so I'll call that y. And then my angle over here, I'll just call it a. So in order to get a, we would just make sure that everything adds up to 180 degrees, or just those have to equal 90. So that means that a is 12 degrees. For the, let's maybe do adjacent this time, I'm going to use cosine. So cosine of 78 degrees equals my adjacent side over 17. So then I just need to multiply 17 to get y. 17 cosine of 78. I'm still in degrees mode, always worth checking. So I get about 3.5. And then to get x, I'm just going to use the Pythagorean theorem, 17 squared minus y squared. So the square root of 17 squared minus y, I'm just going to use that answer button, gives me about 16.6 in this case. There you have it. So I did another problem. You saw another example on how you might solve this. Okay, so the next topic I want to talk about are some special right triangles. You can think of these as, these are really relationships you should have memorized. They're sort of, you can think of them as formulas. Not really memorized because you will be able to use your notes, but these are one of those things that comes up a lot, so this should be pretty easily accessible in your memory banks. So there's some special right triangles. The reason they're special is because the angles are all whole numbers, so I'll put 30 degrees there and 60 degrees up here. And the side lengths are also pretty easy to get and understand. So the side lengths for sort of our parent triangle is 1 over here. This side length is the square root of 3, and then the hypotenuse is 2. And then we also have, and this is called a 30, 60, 90 triangle because those are the angles. And then the other one is when we have equal angles, 45 degrees on each of those. And in this case, the side lengths we can call 1 and 1, and the hypotenuse is the square root of 2. We could go through proofs for these, but I'm not going to do that in this video, where these come from. You probably saw this in geometry at some point. And so the important thing to notice here is really these are relationships. So I think of these as the parent triangles, but really what you should do, sorry, not relationships, but ratios. Really what you should do with these is think of these side lengths as x, and then this side length is x times the square root of 3, and then this one is 2x. So that worked out in the one I just did where I said this side length was 1, this one is the square root of 3, and this one is 2. And then for this triangle, we would say this is x, x, and then this is x times the square root of 2. Again, this works because I said it was, you could do 1, 1, and then the square root of 2 there. Now, also, not just dealing with degrees, you might have radian measure. So something to note is that pi over 6 is actually 30 degrees. Pi over 6 radians is 30 degrees. And pi over 3 is 60 degrees. So we could also do this triangle in radians, and that will come up as well. For 45 degrees, that's pi over 4. And so we also have that relationship here. All right, so what we can do now, and really these problems aren't any different from what you saw before, but sometimes you might have a non-calculator portion of something. So for example, the AP Calc test has non-calculator, and you would need to know these relationships without using the calculator. These problems you will be able to use the calculator for, but anyways, I'll show you how you might do it. So we're going to go ahead and solve these triangles again. And let's go ahead and set this up. So let's say the angle in this case is 45 degrees. And I'm going to say that the adjacent side is 5. So you can fill in the missing information. I'm just going to go ahead and label these X and Y again, and I'll call the angle A. You know that A has to be 45 degrees because this is a 45, 45, 90 triangle. You know that X has to equal 5 because if you look at our triangles up here, notice how these are always equal. X is always equal to X, or when it was 1, it was equal to 1. And then for Y, it's just 5 times whatever the square root of 2 is. And I'm not going to work that out because this is the exact answer, 5 times the square root of 2. But if you needed an actual decimal approximation, you could multiply those. You could do 5 times the square root of 2. And notice you would get about 7.1. But this would just be the answer in this case. There's really no extra work to do because you have those parent triangles worked out. Now, alternatively, you could do, well, sine won't work. Let's do this. You could say, hey, I want to know cosine so that I can get 5 over y. And then you could actually solve for y, and you would end up with about 7.1. But because we're using these parent triangles, you can actually get exact answers, which is convenient. Okay, let's go ahead and try one more in radians. So we're going to do, let's call that the right triangle, that's the right angle there. Hypotenuse, I'm going to say is 7. And then for the angle, I'm going to go with pi over 3 radians. Notice this is not drawn to scale, and I have kind of flipped things around from the parent triangle. Whoops. I just noticed that there's an error over here. That should be pi over 3. Excuse the error. So I've also flipped things around because I put the pi over 3 here. So just keep in mind that the parent triangle in this case is actually going to look like this. And so we basically know that 7 equals 2 times x in this case. Sorry, let me go ahead and color code again. Okay. So first let's label. We need this angle A. We need this side length over here, which I'll call x, and I also need this side length, which is y. All right. Okay. So notice that y, if we're comparing these, y is going to be half of the length of that, because if I did x over 2x in this triangle on the right here, I would end up with a half. So that tells me that in order to get y, I really just need to do 7 divided by 2. And I would get 3.5 for y. X is a little bit trickier, so this right here, it's going to be harder to get these ones. What we have to do is compare these here. So if I did x root 3 over 2x, notice that the ratio is the square root of 3 over 2. Alternatively, you might notice that I could also take whatever this side is and just put a square root of 3 on it. So either way, so one way to do this would be to say that x equals 7 times this ratio. And you would end up with 7 root 3 over 2. Or you could just say, I know that it's got to be that 3.5 times the square root of 3, which really doesn't look good because of those decimals, but that is the exact answer. And so we end up with these as our sides. And then the missing angle A, well, that's going to be pi over 6 because we know our triangles. So once again, these are called the special right triangles, and they do come up quite often on something like a standardized test because they're so well used. But like I said as well, if you have a calculator, you can do all of this with the calculator and not worry too much about it. This is really just for in the future you will be seeing these special triangles, and we will also use them on other content in this class.